G'day guys. All right, so what we are looking at today is geometric series, which will be of no surprise to you probably because there's some symmetry evolving here. What I mean by that is we first looked at arithmetic sequences and then arithmetic series. Then we did geometric sequences. Now we're looking at geometric series. So a geometric series is obviously the sum of the terms in a geometric sequence, just like an arithmetic series was the sum of the terms in an arithmetic sequence, okay? And we had a formula, a nice little formula, summing formula for arithmetic series. We also have a nice little formula for geometric series, and we are also going to prove it. So let's first take a quick look at the formula. To find the sum of the terms in a geometric sequence, the following formulae can be used. And it's the same thing, one's just been organized a little bit differently, but just pick one of them and stick with it. This here, the sum of the first n terms of an I'm going to probably keep making that mistake, of a geometric sequence equals A. So the first term, bracket, the common ratio R to the power of n, minus 1, all over the common ratio R minus 1. All right, but don't take my word for it. Let's prove the bad boy. So here we go. Now we're going to use a very, very similar technique to how we prove the summing formula for an arithmetic series. Bit different though. All right, so the first step is to sum the terms of a geometric sequence, a general geometric sequence, okay? So the sum of the first n terms of a geometric sequence is, well, the first term is A. The second term is A times R. The third term is the previous term, A times R, times another R. So we get an R squared, AR squared. And it goes on in this fashion. AR squared, AR cubed, all the way up to AR to the n minus 1. Okay, that is the formula for the nth term. So that's obviously going to be the final term. And because this is a sum, instead of commas, we've got plus signs, okay? All right, step number 2. Now, you're probably expecting me to rewrite that sum in reverse order because that's the sort of thing, I think that's what we did for the proof for an arithmetic series. But we're not going to do that. We're going to do something slightly different. Now I'm going to take this sum and multiply it by R, the common ratio, which means I have to multiply each one of these terms by R. Everything on the right-hand side has to be multiplied by R if I'm multiplying the left-hand side by R, which I am, see? Okay, so this A here becomes AR. This AR becomes AR squared. This AR squared becomes AR cubed. All right, and all the way up to the final term, AR to the n minus 1. If you multiply that by R and use your index laws, R to the n minus 1 times R to the power of 1, that 1 and the minus 1 cancel out and you get R to the n. So the final term is AR to the n. All right, so I have created two expressions. Sn, the sum of the first n terms of a geometric series, a sequence rather, and a second equation where I have just multiplied the left and the right-hand side by R, which I'm totally allowed to do. Doesn't break any of the rules of maths because I've done it to both sides of the equation. All right, now I'm going to create something new. I'm going to do RSN minus SN. In other words, 2 minus 1, because that's how I've labelled them. So RSN minus SN. So R multiplied by SN, all of the terms in that sum I've written along the top here. this minus sign is here. And all of the terms for Sn I've written along the bottom here. All right. Now, what you need to first realize is that Rsn, that expression, has just as many terms as are in the expression for Sn, okay? Which means they line up in columns. All of the terms line up in columns, and there won't be any leftovers. All right, so what can we do? Well, now we can start cancelling some things out, because this is a positive AR minus this AR. So they disappear. AR squared here minus AR squared here. And so we do all of this diagonal cancelling. Now, it's a little bit hard to visualize what happens here, but we don't end up with nothing. We end up with two terms left over on the right-hand side. Now, just to illustrate what those, well, actually where those two terms would be, I've drawn this silly little diagram here. We're cancelling things in a fashion like this, along a diagonal. And this top element here has nothing to cancel with down here, all right? And this bottom element here has nothing to cancel with up here. So these two are our leftovers. They are what remain on the right-hand side of the equation. And what are those two leftovers actually going to be? Well, AR to the power of n minus A. Okay, so we get R multiplied by Sn minus Sn, that just comes down here, equals AR to the power of n minus A. Just these two things put together. Now that is super neat. It's so nice in maths when everything just cancels out, because you know you're onto something that really, really works. Okay, so now we can do some factorizing, which makes this even nicer. On the left-hand side, we have an Sn here and an Sn there, two terms, so we can take out the Sn, and in brackets, R minus 1 remains. If you multiply that out, you'll get back to this. So that's just factorized. And we can factorize this as well, because the ARN and the negative A terms both have an A. So that is equal to A bracket Rn minus 1. All right, just delete a couple of things there. So we have our equation here, and we're almost finished. We want a formula for Sn equals. So let's divide both sides by R minus 1. So that just goes underneath, and we get, delete, delete, Sn equals A bracket Rn minus 1 over R minus 1. So you can find the sum of the first n terms of any geometric sequence, so long as you have the number of terms that you want to sum to, so n, and the first value, A, and the common ratio, R, as required. All right, moving on. Okay, so question 1. Find the sum of the first 9 terms of the sequence. Well, I should specify the geometric sequence. 1/3, 1/9, 1/27, 1/81, etc., etc., etc. Okay. So A is our first term, which we have, 1/3. To get our common ratio, I'm doing T2 divided by T1, which is 1/9 divided by 1/3. And remember how we divide fractions? That becomes 1/9 times 3 over 1. You flip the second fraction upside down, change the division into a multiplication. So 1/9 times 1/3 becomes 3 over 9, which is 1 over 3. So R equals 1 over 3. And A equals 1 over 3. All right, same number for both. So what are we trying to do? Find the sum of the first 9 terms. So we want S9. So I've written down the general formula first, and then I substitute my values in second. So n becomes 9, a is 1/3, r is also 1/3. Here we have n showing up again, and on the bottom, r, which is 1/3 minus 1, and that equals, and now this is interesting, 0.49997. Now you might think that, oh, that's getting towards 5. There's going to be some n value where it equals 5 exactly. There actually isn't. This is what we call a convergent sum. This is one of the most profound things in mathematics that you learn about much, much, much later, but this is sort of a first glimpse of it. It's possible to get closer and closer and closer to a number forever without ever getting there. So if there was such a thing as S infinity, which there kind of is, but sort of hard to conceptualize doing anything an infinite number of times, then that is what would equal 5 exactly. But if I calculated S 1 million, then I would still get something that is 0.4999999. I'd be here all day saying 9999, but it would not be exactly equal to 5, okay? So kind of interesting little fact there, but it is approximately, I said 5, I meant 0.5. It is approximately equal to 0.5, okay? All right, moving on. All right, question 2. For the geometric sequence 1, 3, 9, etc., find how many terms must be added together to obtain a sum of 1093. So what do we have? We have that a equals 1. We have r equals 3, because t2, 3, divided by t1, 1 equals 3. And we have that the sum to some nth term is 1093. So Sn equals 1093, but Sn also equals this business here from our formula. A times r to the n minus 1 over r minus 1. Okay, so we have 1093 equals 1 times bracket 3 to the n minus 1 over 3 minus 1. So one unknown, but once again, it's a power. So that makes things a little bit difficult, but this is a very, very artificial question. So we're able to employ a cheat. So I'll show you how that works. Okay, delete a couple of things. So this 3 minus 1 equals 2 on the bottom. So I'm going to multiply both sides of the equation by 2 to simplify things, and I get 2186 equals 3 to the n minus 1. I'm trying to isolate the n, so I'm going to add 1 to both sides, and I get 3 to the n equals 2187. And if you're really good with your powers of 3, you will recognize that 2187 is exactly 3 to the power of 7. How convenient. So you can see that this question has been designed for school students. So now we have 3 to the n equals 3 to the 7. And because the bases are the same, then the powers can be equated. So n equals 7. And therefore we can answer the question. So the question was, how many terms must be added together to obtain a sum of 1093? The answer is that 7 terms must be added together. So there you go. Question 4. In the 15-day Tour de Moravia, which must be a bike race, the cyclist must ride 120 kilometers on the first day, and each successive day they ride 90% of the distance of the previous day. So they ride less and less each day, but just by a little bit, okay? A, how far do they ride in total to the nearest kilometre? Well, this is a summing question. We know that there are going to be 15 terms in our geometric sequence, because it's a 15-day tour. And they are not asking for how many kilometers are ridden. Is that a word? I think so. On a particular day, they're asking how many kilometers have been ridden altogether. So we need to be able to add those 15 terms together. So we use our formula. Now let's figure out the elements to substitute into our formula. A is 120, because that's the distance they ride on the first day. And R is 0.9, okay? If you want to decrease 120 kilometers to a value that is 90% of 120, like they say in the question, then you have to multiply 120 by 0.9, which is just 90 over 100, in other words. 90%. So we have A and R, and we have our SN formula, and I've just gone ahead and straight away substituted my values in. So S15, SN, equals A, R to the power of N, and then minus 1 over R minus 1. And I get 952 point something or other, which I've rounded off to 953 kilometers, because it says to do so in the question, the nearest kilometer. Okay, so that's pretty neat that you can do that. All right, part B. After how many days will they have ridden at least half that distance? That distance being the distance that we just calculated, the total ridden over the full 15 days. After how many days will they have ridden at least half that distance? In other words, for what n value is the following true? Sn, a new sum, is greater than or equal to what we just calculated, the total distance over the 15 days divided by 2. So for this new sum, Sn, we need to find n, okay, such that Sn is greater than or equal to that number divided by 2, which it turns out is 476.4653 kilometers. All right, so here's what I do. I simply write that the sum to the first n terms needs to be greater than 476.4653 kilometers. Now I have a formula for Sn. So I replace the left-hand side of that inequality, which is like an equation except with greater than or equal to signs, with this. So I've got my A, R to the N, minus 1 over R minus 1 with the values subbed in. And then my greater than or equal to sign, that many kilometers. Now, quite honestly, at this point, you can pull out your CAS calculator and get it to determine for what value of n, or I should say, for what lowest possible value of n, will the left-hand side of that inequality be greater than or equal to the right-hand side of that inequality. But I've done a couple of extra steps here just to get it down to something that's easier to enter into my calculator. This here, just by doing some simplifying. And I get 0.9 to the power of n less than or equal to 0.6029. Now it's turned into a less than or equal to because up here, 0.9 minus 1, that's a negative number. And then when I multiplied both sides of that inequality by a negative, a rule you might have forgotten, but if you do that, you have to switch the direction of the inequality. So this thing, I just put into my CAS calculator using the solve template. It's just, there's a button for it, solve, open left bracket. And then you type that in directly as you see it, do a comma, and then put an N, or if you want to just use an X, that's fine. And then you close the bracket, and you will get from your CAS calculator that N must be greater than or equal to 4.8 days. But we were asked after how many days will they have ridden at least half the distance, not how many partial days. So they get to exactly half that distance after 4.8 days, but we've been asked for a whole number of days. So we round up. And our conclusion is that after 5 whole days, we can say that they will have ridden at least half the distance from question A. And that is it. Sweet. Just checking. Yep, that's everything, guys. Feel free to email me anytime. I'm barely getting any emails from you guys, which is either a good thing or a bad thing. I'm hoping it's a good thing. That means you're on top of things, but please seek out help when you need it. That's still my job, even though I'm not there at school with you guys. All right. Be well, and I'll see you next time.